Good afternoon. If you are joining me for this video, thank you. We're looking here at the derivation of the exponential derivative function. I am Mr. Ish, and we will be continuing with a few videos regarding these derivative derivations because they are important, and knowing these derivation procedures will make you a better calculus student. If you easily start with a graph of something which looks like e to the ax. You know it usually has an intercept over here 0, 1. If you do a derivation procedure of this in terms of the derivatives using the graphic approach, this right here is my f of x. If you start looking at tangent lines at varieties of these points or various points, you do a tangent line analysis. You've seen a video on that, graphic determination of derivatives. You can always look at that. And you look at these points. Here's one point right here, here's another point, another point, another point. You plot the points with regards to your tangent line values, your slopes of those tangent lines. You can get a very similar graph show up for the derivative. What does that tell you? That the derivative of anything which is like this is very well equal to that. It just ends up being a e to the ax. But you can see this part right over here very well mirrors that part. The a is just a coefficient which happens to show up that can either affect the vertical approach of this curve, whether it's upwards or downwards, depending on if it's a fraction here, less than 1, larger than 0, or if it's a coefficient larger than 1. You can see all of those things show up. But the graphic procedure here is easy and it's subjective, but it does lead to a relatively accurate derivative outcome. What we want to look here is at the more precise and accurate determination method for the derivative of this, and that's the limit approach. And I'll show you, and the rest of the video will be focusing on that limit approach to this derivative derivation. The limit approach is by no means hard. The f of x looks like e to the ax. We have to find the derivative of this, and we use this basic definition of a derivative, f of x plus h minus f of x over h. But prior to doing this, we have to do one simple task, because within this, as we take it forward, we have this assumption which will come into play. We have to solve that assumption right now so we can utilize it in this approach. If supposedly y is equal to ax, e to the power of ax, you are looking at this function in terms of its derivative, and you were to employ the natural log, you can literally bring this exponent and then you can bring in the natural logs, right? Ln y equals ax ln e. This is 1. You do implicit differentiation of this. You'll have, after the derivation procedure of this, you'll have 1 over y, and you know you'll have dy over dx. You know implicit differentiation. The derivative of this will just be a, because the x vanishes with the derivative of that. D over dx, x is equal to 1. Then dy over dx, which is the same thing as saying y prime derivative with respect to y is equal to a y, because you've cross multiplied y. And you know what y originally was, that, and a e to the ax. So here, using the natural log properties or the properties of logs, you've shown the derivative of this to be that right here. Y is equal to that, this y prime derivative with respect to y is equal to that. We just are showing you this derivation procedure using the limit formula, the basic definition of derivative, and this right here will come very well into it. Keep this little procedure here in your mind because we will utilize it. Continuing from this step, this is my f of x. How do we play this? We have ea into x plus h minus eax over h. You know, limit h approaching 0. Open this up right here, the parentheses, limit h approaching 0. We have eax plus ah minus eax over h. You can rewrite this as how you can imagine using the properties of exponents, same basis. When you multiply them, their exponents add. You would really be looking at eax, eah minus eax over h. But you see this, you combine this, you'll end up with that. Isolate e to the ax. You have limit h approaching 0, e to the ax. You have e to the ah minus 1. I'm bringing the h under this. Everything is good. There's no fancy manipulation going on in here. Everything is good. Separate everything under its individual limits. This expression and this being multiplied, separate out. The limit of an expression is equal to the individual application of the limits of their substituents. That's a limit property you can utilize. Limit as h approaches 0 is equal to e to the ax times limit h approaching 0. You have all of that, e ah minus 1 over h. This right here is an expression for which, if you would be placing the 0 in places of h, you would get a indeterminate limit form come into play. think about it. You'll do 1 minus 1 over 0. You'll have a 0 over 0 and indeterminate limit form. So you can use the L'Hopital's rule procedure. You can do the derivative of the numerator. You can do the derivative of the denominator. If you were to do that, you would get ae to the ah over 1, and you could literally plug 0. And how did I get this? From that natural log procedure I just showed you prior to doing this. That's exactly what we got using the natural log procedure. So that's why I told you that, and I told you to keep that in your mind. When you plug 0 in place of the h, you'll end up with just getting an a. From all of this, as you're seeing, we're getting an a. From all of this, limit as h approaches 0, e to the ax, I'm getting e to the ax. When I multiply these two, you know what we end up getting. We get ae to the ax, which is the derivative of something which looks like e to the ax. And what have we done? We finished this procedure, and it wasn't too hard. Perhaps the hardest part was just this part right over here. Or maybe another part might have been recognizing that this part right over here is equal to all of this right here. And you could have then isolated e to the ax and created another expression, and then separate everything into the product of individual limits. But everything else follows, as you see, and the derivation procedure has been completed. So keep this derivation procedure in your mind and remember it. It's something you could be tested on, and it's not hard. Just do this a few times on your paper and it'll become part of your memory. Thank you for watching. Stay tuned. Have a nice day.